Okay, folks, this is the lecture on angled forces or crooked forces or vector breakdown, however you want to title it. All right, so crooked forces are doing two things at once. So up to now, we just said, the force is to the right or the velocity is to the right, so that's positive, or it's to the left, so that's negative. And we could get away with just having positive and negative indicate direction, even though that was kind of confusing. Now we're going to look at forces that are crooked, and it means that they have a little bit of force to the right and a little bit of force up. And this is called being a vector. In math, you put a little arrow over the variable to represent that it has at least two dimensions. It's going over and up. And then, if you did more, if you wanted to, you could do three dimensions and just adds one more dimension. Okay, so this is vector A, this is vector C, and then this dark blue vector is the sum of those two vectors. So don't worry too much about the sum right now. We're just focusing, this lecture is just focusing on what's called vector components or vector breakdown. But since the diagram is here, what that does is if you have two vectors, if you're pushed in the direction of A and simultaneously pushed in the direction of C, so if I had two fans and one was pushing really hard, vector A, and then another fan down here that was pulling it completely vertical, I could get rid of both of those fans and replace them with this single dark blue S vector. That's what it means that S is the sum of these two, is that it's equivalent to having these two fans. Since C, you can see, is kind of canceling some of A's downward force, it's equivalent to having just that dark blue. Okay, a couple of other things, just in case you see it in other textbooks. This absolute value means take the magnitude of the vector. So vector C is 10 units long. I want to go to A. You can see that A has a length or a magnitude of 24.8, whatever that is. If it's force, it's at that many newtons. The angle is 43.4 degrees, and it is going over 18. Let me get rid of these other vectors. Vector A is, oh, interesting. Sorry. I thought, so you can go back and look. I don't know why it turned that off. Components. So vector A is going over a certain number and up a certain number. Okay, so that's what we're going to be looking at. This angle, how far over and how far up. All right. Apologies for wasting your time. Okay, let's keep going. Okay, so crooked vectors are doing two things at once. And I got these diagrams from a link that's at the end of the slide deck. So there's two ways to look at it. They are equivalent. You can think about, so the black vector is something being pulled diagonally or crooked. It is magically pulling horizontally with a strength Fx and pulling vertically with a strength Fy. So I like this diagram better because you can see that both of those forces are happening simultaneously. But again, the green and the red vector could be replaced with this single black vector if you want the same job done. Okay. However, when we analyze diagrams, we tend to draw the vector breakdown like this, where you're going to have, this could be a rope that's being pulled crooked. And you're going to know this angle, and this reinforces that you've got this beautiful right triangle, and in 2 seconds we're going to do trig identities. So this is what we're going to draw. But it's not like we pulled to the right, and then pulled up. They are both happening simultaneously. Okay, so quick review of SOHCAHTOA. You can pause the video if you want to write this stuff down. I think you've seen this before. So again, pause and write down anything you want for SOHCAHTOA. So this is what we're going to do. A, for whatever reason, and again, I stole this from the link at the end of the slide deck. A is, I guess, A for angle. All right, so you're going to know an angle. The actual force is always the hypotenuse. All right, so please write that down. The actual force is always, always, always the hypotenuse. So if we say that, the rope is 15 newtons, that is the actual force. And then you'll know the angle. Okay, and then this Fx in this case, because this angle is your adjacent, this is your opposite. So you can see that I'm just going to walk you through this once, and then we're going to learn a goofy mnemonic, that sine of theta, which is A, is opposite over hypotenuse. So sine of A is Fy over F, where Fy is how much of that force is pushing up. Generally, you know this, and you're looking to figure out how much of that is over and up. So we're going to solve this for Fy. So we're going to multiply both sides by F. And Fy is F sine of A. Okay, that's what they're doing here. And then you could do the same thing for cosine, and then solve that for Fx. Okay, so this is just the SOHCAHTOA stuff from 2 slides previous, but with physics context, so that instead of hypotenuse, it's the force. Okay, do you want to have to set that up and draw your triangle and do SOHCAHTOA over and over again? No. You could, but it's just going to cost you time. So this is my goofy mnemonics. Given that you know the angle relative to the horizon, okay, like this is the positive x-axis. Given that you know that angle, my goofy mnemonic is stop signs are vertical. So, and here again, instead of force, they're saying the magnitude of the vector, which I left because I think that is a good for you to be comfortable with that terminology. But the vertical component is going to be F sine theta. The up and down component is F sine because stop signs are up and down. And then since coastlines are horizontal, your horizontal component is going to be the cosine of theta. That's going to work for you 99.9% of the time, all right? But I just want you to be on the lookout for, there's a couple times, if you take the AP, they love to label the wrong angle because they don't want people just memorizing a bunch of equations and not understanding, oh, which angle is important, like should this be sine or cosine? But there's a couple of times where like you're hanging a picture from, and there's 2 ropes, T1 and T2, and I have labeled these angles because there's too much else going on in the diagram. So to me, I'm like, oh, I'm just pointing, this is the angle that's easiest for me to label for you. Hopefully you can see that that is the, quote, wrong angle. That this angle here is not relative to the horizon. Okay, so I'll teach you another goofy mnemonic if you want. Well, I'm sorry, I'll do it right now just so you know, instead of just referencing it. The mnemonic that's always going to work is find the angle that you know. Okay, the actual vector is always the hypotenuse, so there's your force. We know this angle. That angle definition is making contact with this blue leg, right? It's not even close to the green leg. That angle is making contact with one of the 2 legs. Contact means that's your cosine. And then the other one is your sine. So that's always going to work for you. Is the angle that is defined is making contact with a cosine term. Okay, which I'm just memorize it because y'all know where that came from. It came from SOHCAHTOA. Okay, and then I just wanted you to have one more visual that the actual vector is force. You don't always know this angle, but often that's what they give you, and that one component is F cos theta and one component is F sine theta. In this case, this is positive and this is positive because they are both going to they're both in the positive direction. I looked and looked for an example, couldn't find one super quickly, so we're just going to go over this together. If the force is in the third quadrant, then your Fy is negative. You have got to put the minus sign in yourself. This is minus F. Let's assume that's theta. This is minus F cosine theta because that is pointing to the left. And this is minus F sine theta because that's pointing down. All right, so in this case, both of them are positive. In this case, both of them are negative. But if you were in the other quadrants, if you were in the second quadrant, then you would have minus F cos theta because it's pointing left, but positive F sine theta because it's pointing up. Okay, so you've got to put the minus sign in. You have to make it plus or minus sign decision twice. Okay, what's labeled is always positive because it's just telling you the magnitude. Because as you can see, it's pointing to coordinate x comma y, and each of these is individually defined as positive or negative. So the absolute vector can't be positive or negative because it's hiding two separate variables that each have their own sign. Okay, hopefully that makes sense. The magnitude's always positive. All right, so then we're going to do a practice problem. So determine the horizontal and vertical component of person A's force. So person A is pulling, which is F2, which is kind of confusing. Oh, because I think I labeled it. Never mind. Person A, which is F2, has a force of 80 newtons. Person B, which is F1, has a force of 120. So what do we want? We want the horizontal and vertical components of person A's force. So set up your SOHCAHTOA, and then we'll check work with each other. All right, here is the worked out solution. So the person A is pulling with 80 newtons crooked, and part of their force is to the left, so it's negative. And so the whatever this is, horse, mule, is being pulled to the left by person A with a force of minus 20.7 newtons and pulled down the road with a force of 77.3 newtons. All right, hope that worked out for you. Couple of warnings. Check your work. So first of all, you want to be in degrees, not radians. So check the mode on your calculator to make sure you're in degrees if those numbers did not come out right. And you got to put the minus sign in yourself. Check your work. Since 75 is way bigger than 45 degrees, the vertical should be bigger than the horizontal, right? 77 is bigger than 21. If it were a more shallow angle, if it's under 45 degrees, then your horizontal component should be bigger than your vertical. Okay, so good way to check your work. And then the final thing to do to check your work is you can do this squared plus this squared that square root equals 80 newtons, right? Pythagorean theorem. All right, so crooked vectors, basically pushing a little bit to the left and a little bit right, and we need to keep them separate because we're going to see that left and right don't affect up and down. They are independent, right? You can run as fast as you want down the football field, and it's not going to get you left and right. You can move as fast as you want left and right, and it's not going to help you head towards the goal post. Okay. Hopefully that makes sense, and we're going to get lots of practice with this. So thank you for listening.